Are there any questions? Okay. According to the calendar, there's an oral quiz. Chapter 7. I can do that later. Yep. I'll put your face down out of habit.
Good start.
Yeah, go ahead.
That's the only thing we figured out. Because at first I got like 11 meters or something.
All right, any questions?
I can't read it.
Yeah.
I was like, I can't read this.
All right, so I've got a spring here, ideal spring. Laying down, nothing on it, and this distance here is, let's say, 0.5 meters. I add a mass to it. And we'll let the mass be 0.4 kilograms. And this is now stretched 0.7 meters. Both of these are in equilibrium. And then I pull down and I let go. The mass is still 0.4 kilograms, and I've now stretched it to 1 meter from the top. It's an ideal spring, so it obeys Hooke's law. And Hooke's law says that the elastic force is equal to the negative of some constant times the displacement from equilibrium. So if I want to figure out the spring constant of the spring, well, in this situation number 2, what are the forces acting on the mass?
Weight and tension.
We're going to be more sophisticated than that. Yeah,
Or
weight.
elasticity.
Yeah, elastic force. Now the negative sign here is just indicating its opposite direction of the displacement. It's stretched down, so the force the spring exerts is upwards. This is going to be proportional to how much it's stretched, delta K, or sorry, K delta X. And that's going to be equal to mg. So I have K delta X equals mg. And therefore K is just the weight of the object divided by how far it got stretched. So 0.4 times 9.8 divided by 0.2. So that's 0.4 kilograms, 9.8 meters per second squared, and 0.2 meters. And we get 19.6 units.
Kilogram meters is.
You answered out the wrong thing.
Oh. Kilogram second squared.
You'll have to word out.
Did I miss per?
Yes. The anti-disease. All right, it's kilogram per second squared. Or, since a kilogram meter per second squared is a Newton, 19.6 newtons per meter. Now, I want to figure out, if I stretch it down this part, what is the acceleration of the mass? Let's make it a vector here. So we're gonna go through our classic facades. When I pull it down here and I let go, what are the forces acting on it?
Weight.
Okay.
Elastic.
Yeah. The same two forces we had before, it's just that it's not in equilibrium. All right, so I have F subscript E minus W. Oh, let's go through the steps. So there's the force diagram. Acceleration is going to be in which direction? All right, I saw the finger pointing upwards. Coordinate system, or axes. What do you want to make the positive direction?
Up.
That seems like the simplest one. I know acceleration is upwards also. Do we need to decompose anything?
Nope.
That was a no?
Yeah.
Okay. Yeah, that's right. I mean, all the forces are either parallel or anti-parallel to our positive direction there. And equations of motion. All right, so the equation of motion.
F is equal to MA.
Minus weight.
Oh,
Yeah,
F minus
this-
this.
FE minus W is equal to MA. If we get a positive value, then A is indeed in the direction we assumed. If we get a negative value for the acceleration, then, oh, it's in the other direction and something seems off. All right, so I know this is equal to K delta X minus MG equals MA. So I know we figured out K is 19.6. Actually, let's go ahead and solve for A. A is equal to K delta X minus MG over M. And now let's plug and chug. So K is 19.6, we figured that out already, meters per meter, or kilograms per second squared. I'll leave a blank right there, my mass is 0.4 kilograms. My acceleration due to gravity is 9.8 meters per second squared. All of that over 0.4 kilograms. The reason I leave this blank is, what is the displacement from equilibrium?
Point five.
Three. It's one of those two.
Oh. Point three. Yeah,
Keep it up so soon.
just because, the spring on the left, I thought that was the equilibrium, but it's not.
Well, actually, the one on the left is an equilibrium. The one in the middle is also an equilibrium.
Yeah, but it doesn't have the mass on it. The spring.
Okay. So there seems to be a groundswell for 0.3.
Yeah.
Anyone want to go with 0.5? It's actually 0.5.
What?
Should have stuck to your guns. Now, what's going on there? Well, let's do it again, except, we'll actually come up with the answer, but we're gonna do this again, except we're gonna stick in just the generic letters and watch the difference between if you choose this to be equilibrium and it's stretched a ½ meter, or this to be equilibrium and it's stretched 0.3 meters. There's another difference that shows up over there. So actually finishing this, we end up with 9.8 minus 3.92 over 0.4, which is 5 point. .88 over 0.4. And we get
$14.7.
units.
Newtons times meters per second squared.
Meters per second squared.
Not newtons per second squared.
Yeah.
What, I heard a couple other voices.
Meters per second squared.
Yeah, meters, it's acceleration.
Yeah.
That's meters. So the meters would cancel out over here. So we just have newtons, kilogram meter per second squared, which is a newton. So ultimately newtons per kilogram or meter per second squared. All right, so let's resolve this issue over what is equilibrium. I'm gonna call this x1, call this x2, and call this x3. So we first found k. K is the change in, so it's k times the change in x, which is x2 minus x1, is equal to mg. So k is just mg divided by x2 minus x1. If we plug in chug, we should get the same answer that we had before. If I go to that second situation there, I have k delta x. So I have k times x3 minus x1 minus mg is equal to ma. Well, x3 minus x1, that's just k x3 minus k x1 minus mg equals ma. Which is, in the next step, might seem a little bit bizarre. Hopefully why I'm doing it will make sense in a moment. That's minus k x2 plus k x2 minus k x1. So all I did was just subtract and add the same thing. Minus mg equals ma. This right here is k x2 minus x1. And this right here is k x3 minus x2. And that allows people to catch up or ask questions or point out mistakes. Now, k times x2 minus x1, we just did that right here. K times x2 minus x1 is just mg. So k2, or k times x2 minus x1 minus mg, that whole bit right there equals 0. And then in the end, we're left with just the spring constant, x3 minus x2, is equal to ma. So what this means is x3 minus x2 is just how far this stretch, that's the 0.3 meters. But if we were considering this to be the equilibrium, then weight disappears. If we want to bring weight into it, like we did right here, then the equilibrium is from before any weight is added to it to the stretch. You get the same answer either way. So if stretch is from equilibrium with the mass on it, it's just the elastic force is equal to ma. If your equilibrium is the spring with nothing on it, then you take the whole thing into account and you have to include weight. And the same thing is true if you brought energy into it, which we will at some point. And let's do that now. So we figured out the acceleration when I stretch it down to that far point down there. Our initial acceleration was some number that was written over in the lower right hand corner.
14.7.
Say it again.
14.7
14.7.
meters per second squared.
At what point will the acceleration be zero? I mean, I pull it down to here, I let go, initial velocity is zero, acceleration is positive, it will start to move up. Where is the acceleration equal to zero?
When it comes back down after, like the point where it turns around.
If the acceleration were zero at the point where it turns around, then it would stop moving. Because at the point it turns around, velocity is zero.
When it goes back to equilibrium?
Which one? First one or second?
Second one.
Yes. We can look at it from this point of view. X3 is how far it's stretched from, is where the object is. X2 is equilibrium. Acceleration is zero when those are equal to each other. So when it gets here, acceleration will be 0 meters per second squared. And so it's being pulled upwards until it gets to here. At that point, it's being pushed downwards. And so acceleration becomes negative. The acceleration will stay negative as it turns around and be negative till it gets to 0 again, and then it's positive then. And on forever since it's an ideal spring. How fast is it going when it passes equilibrium? When acceleration is 0, how fast is it going? Well, let's solve it more than one way. First way I'm going to solve it is energy. So looking at case number 3 over there, I've got, so this is equilibrium here, so where acceleration is equal to 0. This is the initial position. That distance was 0.3 meters. The elastic force is a conservative force, energy is conserved. So if I can figure out the energy here, I know the energy there. Actually, I know the energy everywhere.
Wait, so, but backing up a little bit, why did you say that like the elastic force is negative K, change in distance?
Change in position.
And then you used the positive.
The negative is indicating direction. So since it was pulled downwards, so delta X is in that direction, that meant FE was up. And so I took that negative sign into account when I put FE in that direction. All right, so that's a conservation problem, conservation of energy problem. What are my 2 types of energy?
Kinetic and potential.
Yeah. So energy initial equals energy final. Yeah, kinetic energy initial plus potential energy initial equals K final plus U final. I'm about to ask that question. Let's just go ahead, do it.
K equals 1/2 mv squared.
and all of you have heard it now. Let's see if we can do it in unison, chorus of angels. What's the formula for kinetic energy?
One half V squared.
Not quite the chorus that I was hoping for. What's the formula for potential energy?
Which one?
Thank you. The one associated with weight.
MGH.
We have two different potential energies here. I'm gonna erase this. We need some extra room. And I guess, so we got 1/2 mv squared. Now the question is, are we bringing MGH into it? If we consider this to be our reference point in terms of how far the spring is stretched, then we have to bring MGH into it, just like we had to bring MG into it. If we're considering this to be the point, where then MGH doesn't show up. And what you should have said when I said one associated with weight, you should have said, no, that's not the way we're doing it. You missed your opportunity. So the only force, since we're ignoring weight would cancel out, what we're left with is the force, the potential energy associated with a stretched spring, an ideal elastic material. What is the formula for the potential energy of an ideal elastic material?